Okay, so welcome everyone to 1W-MINDS seminar today. This is the first 1W-MINDS seminar in this alternative time slot in the new year 2021. So happy new year to all. So today it's my great pleasure to have Professor Raymond Chen to speak in this seminar. Professor Chen is currently a chair professor at the Department of Mathematics and a vice president of City University of Hong Kong. So Professor Chen is a leading expert in computational mathematics, numerical analysis, scientific computing, imaging processing. Professor Chen has won numerous awards, including Leslie Fox Prize for Numerical Analysis, Funcom Prize of Scientific Computing, and he was also elected to SIME Fellow in 2013, an AMS Fellow in 2021, and a member of SIME Council. He has published over 150 research papers and 3 books. He is also serving or have served on the editorial board of many international journals, including SIME Journal of Scientific Computing and Imaging Science. So today, it's my great pleasure to introduce him to our seminar. He will talk about high-resolution phase reconstruction in ground-based astronomy. Now, let me give the stage to Professor Chen.
Thank you, Yang, and also thanks to organizers for asking me to give a talk here. It's my pleasure to be here. So today I will talk about this high-resolution phase reconstruction in ground-based astronomy. So let me Oh, okay. So this is the outline of my talk. So I'll give a background of ground-based astronomy, and then there are 2 types of telescope. What the first one is that those are so small one that we may be able to move that to get a high-resolution images, and then those are the second part is that those are the big one that it is impossible to move them. Okay, but then we can still get high-resolution images out of this using our method. Roughly speaking, the second part is what we call the open loop telescope, and the third part, the last part, is what we call the closed loop telescope. Okay, so what is ground-based astronomy? So basically, the idea is that we want to observe something in space, for example, this satellite, using a telescope on Earth. Okay, so if you let me denote this satellite as a true image fxy, and then if you take the image using some telescope on Earth, then that's usually what you observe. It's very, very blurry, and the reason for that is that the air is moving in between, and then we have this turbulence. Okay, that creates some blurring. In fact, we learned it when we were very young, even in kindergarten. We sing the song "Twinkle, Twinkle, Little Star." So supposedly a star from very far away should be what you will observe it on ground. It should be like a pond, right? One pond, because it's so far away. But then if we observe it not only by telescope but by our eyes, then we see that it twinkle, twinkle, right? The twinkle, twinkle, little star. So in fact, a pond or star, okay, from far away, when we observe it on Earth, we see something like that. The pond source is spread over, okay, in a large region, and this function or this image is called the pond speck function. It's because of the turbulence of the air in between. Okay, so because of this, actually every pond on this satellite is kind of blurred by the same blurring function KXY. So that's why we get this very blurry image. Okay, and in ground-based astronomy, so basically the idea is that given this GXY that we observe on the ground-based telescope, we want to get back the true image. Okay, so that's the problem for us. Okay, mathematically, it can be posed into a very simple equation. So basically, the fxy, the true image, the satellite image, is being blurred by this convolution kernel, the pond speck function, and then with some unknown noise, then we get the observed image. So this K is the PSF, pond speck function. And the problem here, of course, both K and F are known, and of course N are also unknown. And then what we have is just G, right? So we want to get F from G. but everything here are known. Okay, so if you put that F this image into a concatenate into a column vector and G the same way, then actually this become a kind of a matrix equations. Basically, this K become this function become a matrix. We call it this matrix as a form, special form. It's called the Bloch-Turbis block matrix. And actually, I have done this for a long time ago. So if the K is known and then G is given, then you can, of course, you can solve for F by minimizing the noise. It's become a least square problem, and then you add some vectorization. It becomes a very standard problem, the variant problem. If K is known, okay. In fact, back in 1993, me and Jim Nagy and Professor Bob Pemmons, we already have a paper on how to solve it if K is known, okay? And basically, we use what we call the circulant preconditioner to solve this kind of matrix equation very fast. And all these ideas were summarized in my science book back in 2007. Now, but of course, for this ground-based astronomy, so the problem for us is that K is unknown, right? So K is the atmospheric turbulence is unknown. So then we don't have this K here. Now, then how do we get the K? So Xu told me that he has done some bind deconvolution before. So one typical example is so we can do something like that. Supposedly, suppose we already have some estimation of F. Let me call it Fi, so I iteration of F. And then now if F is given, if G is given, then you look at this. Basically, this one is symmetric. So then we can, if F is given, G is given, then we can do a least square problem and to try to find the K. And we can add some constraint on the K. Now, then we get this K, okay? Once we have the K, then now K is given, G is given, then we can iteratively update the F, okay? So this is kind of bidirectional iteration was first proposed in Tony Chen and C.K. Wong, okay? So this is one way to do it. But another way to do it is what we can reconstruct this K by using some other means. One means is so basic what we call the lateral guide star or artificial guide star. So what is lateral guide star? So let me go back to this picture here. So suppose we want to get this satellite image, and we don't know the point square function. Now suppose there is a star just behind this satellite. Then we can take a picture of the star, right? So and then to get the point square function. Then this star will be called a lateral guide star. So then we should using the star image, then we can get a point spec function out of it. And then K will be known, and then hopefully then we can solve for the if K is known, then we can solve for this F using a standard least square problem. But then if there is no star behind, then what we can do is what we call the artificial guide star. So the idea is that so we shoot a laser up into the sky to burn a point in the sky. And then we observe how that point is the bird, okay, on our telescope. So this point is called the artificial guide star, okay. So in fact, this last year, Nobel Prize in Physics, well, half of it was given to this group of people, and then they are the pioneer in proposing this artificial guide star. So this actually this laser can shoot up to very high, high altitude. Okay, so well, in fact, this so this is one image that at that time was done by my collaborator. So using the artificial guide star idea. So this is the bird image, and then you use the artificial guide star then to get the point square function, and then from that then you debird the image, then you get something, which of course is not very nice, but then it's much better than this already. Okay, and in fact you can also get something like that. This is the Hubble telescope, and then they can do something like that. Okay. Now this one was mentioned in Siam News back in 1996. Well, in that article, so the title of the article is "What does the government get for its investment in basic research?" It mentioned that basically, my collaborator, Professor Bob Hemmons, he testified before the Congress, and this House Appropriation Committee, and tell the government why they have to invest in basic research. And then he precisely used this example, the satellite image, to show the government that this kind of research are important for the US. Okay. And in that time, so basically, Professor Hemmons is using this result to show to the Congress. It's a frame by frame deconvolution using the artificial guide star to get the point spec function. But what today I'm going to talk about is that so this is only frame by frame. But can we do something better? Okay. So this is what you will see later on. So if we have this even much better than this one. But then we get a much better result, okay, out from it. So how do we get it? Basically, the idea is to use multi-frames, okay? So multiple images, like you see here. So actually, you have multiple images, okay? So we hope that by using multiple images, then we can get something much better than this one. So that's the aim of this talk. Okay, well, in order to get the point spec function, we actually use another approach, not directly of taking the image of the point spec function from the electrical guide star or artificial guide star. So we actually measure the obtain the point spec function by measuring something different. So let me explain it now. So when the light from let's say a distinct star, a distant star from very far away, when they come to Earth, before they hit the Earth atmosphere, then basically you can consider them as a planar wave, okay, because the rate is too long, right? And then but just before they hit the Earth surface, they pass through this atmospheric turbulence, and then they become wavy, okay, because of the turbulence, okay. So now then we call this deviation from the plane from the straight line. We call it the phase or the wavefront. Okay. So I denote it by phi. Now the nice thing about this is that if you can measure the phi, okay, then you can actually get the point spec function by using this Fourier optic formulas. So the idea is that so if you can measure the phi, and if it is your telescope, the aperture of the telescope is W. So because you can only see this part of the sky, then if you can obtain this part of the phi in this aperture, then you can just compute this one, take the inverse Fourier transform, and take the absolute value square. Then you get the point spec function. So then the main idea now then is that so you don't need to take a picture of the guide star or artificial guide star or electrical guide star, but all you have to do is to measure this wavefront. Okay, if you can measure this wavefront, okay, this phi, we shift it onto your telescope, then actually you have the point spec function. And then once you have the point spec function, as I mentioned before, then the problem becomes a standard least square Topic least square problem. Now the question is, how do we measure the phi? Okay. So there is this what we call the waveform sensor to measure this. The waveform sensor is designed like this. So basically, this waveform is coming, and then they pass through the lens, and then they focus onto a imaging plane. Now, if the waveform is flat, okay, if there are no distortion, then this point, this focusing point, should be at the center of this square, okay. But because of the waveform is not flat, okay, so then these points will move away from the center. And the displacement of these points from the center, I call it x or y, okay? The displacement in x direction and the displacement of y direction in the ij square. So basically, it's a measurement. You can measure this displacement, but then this measurement also indirectly give you the approximation of the derivative of phi, okay, over this this square, okay, the particular square. So you see that. So actually, the problem for us is that so we cannot measure the phi, this up and down directly, but what we can measure is the derivative of phi, okay, the derivative of phi. So the wavefront sensor that we can have is that, so the wavefront sensor does not measure the wavefront, but it measures the somehow like a derivative of the wavefront. Okay, it's called the there are two types basically. I'm just telling you one type here, the Sharp-Hartman wavefront sensor. Okay, so of course now you think that, okay, so the way well, we cannot measure the phi directly, but then we measure the wavefront by the wavefront sensor, but we can only measure, for example, the x derivative of the wavefront or the y derivative of the wavefront. So these are typical phi, okay, and then this is gradient, okay. Okay, so you see that so dx and dy here are the first order derivative modeling the sensor. So basically this operator here, okay, this is the d, okay, the dx and dy. So you see that so we cannot measure the phi directly, but we can measure the px and py. But then you think that, okay, so it's still a very easy problem, right? Because once we have the derivative, then we can do the integration, and then we can get the phi. Once we have the phi, then we can get the Pons-Beck function, and then we can solve the Toeplitz least square, and then we get back the image. But unfortunately, there is still one complication. The wavefront sensor, okay, it collects log phi, but then the derivative of phi, but then it collects it on a very coarse grid. So for example, this is the phi, and then the wavefront sensor, they collect something like that. So it's a very low resolution wavefront image of the derivative. The reason for that is that so it's not enough light to collect to be collected. So then the pixel or the wavefront pixel cannot be too small. Okay, so then in the biggest telescope that we are going to build, actually not yet built. Okay, so this wavefront sensor the resolution is like 80 by 80, something like that. So it's not a big high resolution picture. So that means so if you get these images or measurement from the wavefront sensor, and then you do the integration for this, then you don't get a very accurate phi. And then if you don't get a very accurate phi, then you don't get a very accurate Pons-Beck function. So that's the problem. So that's the major problem actually. So then what should we do? In order to get a good images, good image out from the telescope. So this is the wavefront sensor. Okay, it's very low resolution. So our idea is that so we want to get a high resolution wavefront from the wavefront derivative from it, and then but then how do we get it? So we only have the low resolution. Okay, so the idea is that so we use a sequence, not only one image, but a sequence of low resolution images. Okay, something like that. And then we hopefully try to create a high resolution image out from it. Okay, something like that. So once we have a high resolution derivative, then we can of course do the integration to get the phi. And then once we get the phi, then we use a Fourier optic formula. Then we get a very good K. And then when we have a very good K, then now we can do a standard Toeplitz least square problem to get a diverted G to get the F. So that's the whole idea, okay? But then now the question is, how do we get a sequence of low resolution wavefront sensor measurement? Okay, how do we get this? So there was a paper that's proposed in this paper. There was a idea proposed in this paper. So basically, this is a low resolution wavefront sensor, gradient sensor. So it measures the wavefront gradients. But then now the idea is that we move the telescope, okay? Now, if we move the telescope, then on the overlapping domains, then we have more sampling points of the wavefront gradients. Then hopefully, then we can do high resolution out of it. Okay, so that's the whole idea. And then, of course, we assume that within this short interval, then this phi does not change. And usually, this time interval is like usually like a millisecond. Okay, so for the whole duration. So we assume that during this motion or the moving of the telescope, the phase does not change. So this is called the Taylor's fusion flow hypothesis. So of course, this idea is not new. So for example, here, so you see that we have a video, and this video is moving, or we move the camera. So then now, actually, in each second, you will have like a 25 images of this. For example, this number here. So now the question is, can you combine this all this information in this video to get a better estimate of this number? Okay, so if you just take one image, okay, it's low resolution and you basically cannot get anything. But then, as I said, so because it's a video, so you can in each second you get like 30 images of this number. So can you combine them together? So the idea is that yes. So actually we have done that. So we use 21 frames in this video, and then we get the from here to here. Okay. So we use what we call the type frame ideas to do it. So of course the idea is that, so in order to do it, then you have to align the frames, okay, in the video. So you have to get the displacement correctly, and then combine the information using some kind of vectorization, okay, to do this. So that's how we did it in this paper. In fact, so we recently also have another idea. So using so this is another video. This even much lower resolution than the bookshell one. So if you just take one image out, then basically you cannot see anything, even the words here. But then if you use the time frame that we did, so you can see the word here, but then this is not very clear. So but recently we use a low rank nuclear alarm to do this, to align this and then try to get this. And now you can see that even these numbers is very clear. Okay. So what I'm trying to say that is that so this kind of moving getting a multiple frame to get high resolution is not new. Okay, so but now we are applying it to the telescope. Now in order to do this, we have to know okay, exactly how the low resolution images and the high resolution images are related. So let me just write down the model. So remember that Px and Py, they are the high resolution waveform gradients. Okay, the d phi, dx phi, and dy phi. Okay, so something like that. And so we want to get this, okay? But what we have is just the low resolution of this, okay? So how do we get from the high resolution to the low resolution? So basically it's like this, right? So you have the high resolution waveform gradient, and then now the AI is the motion operators, because we move the telescope, okay? So each time we move the telescope, then we have a one motion matrix, okay, to move this. And then W is the apertures, because we don't see the whole sky, okay. And then you downsample it, then you get one image, one observation on the waveform sensor. So that's how we get the multiple waveform sensor from one high resolution waveform gradient, okay. So now this is the model. So these are the observation like this, and these are the one that we want to find, okay. Now we have a clear model here. So all you have to do is to do the least square, right? So we just put it on the outside, and then now we have this least square problem here. Now, of course, this downsampling operator is singular, right? So then you need some kind of vectorization. So in James' first paper here, so they use this L2. So these are taken off vectorizations. So given the Q, so this low resolution waveform gradient measurement, and then we try to get the high resolution waveform gradient. Okay, so then this is a L2 problem. So then in order to solve it, then you have to invert the matrix. Right? So this is the matrix that you have to invert. And then, but then we observe that basically this Px is Py is the derivative of phi, right? So then it's basically is the L2 norm of phi. The grade this Laplacian of phi. So then it will kind of smooth out the phi. So then in our paper, so our first paper in this direction, so we kind of replace it by the L1 norm, okay. The L1 norm, the total radiational norm. That means we use the one norm here, which is more or less equivalent to this one. And then we get a slightly better result. Okay, so this is the model in this paper. But now you observe that either this model or the previous one, this model, after you get the Px or Py, remember that they are the gradient, the waveform gradient, right? So you still have to do an integration, okay, to get the phi. Okay, so that's what I mentioned here. So with the measurement, you try to solve it, Okay, so px and py, but then even if you have px, py, then you still have to get the integration, right? So what then we propose, so why don't we just put it inside? So we have the measurement here, and then we directly solve for the phi, right? So it's easier, okay? So we don't have to break it into 2 steps. So we can actually solve it like this. And then now we can directly regularize the phi, right? So depending on what phi you have, okay? So typically, for people doing this kind of thing, so they will use the covariance of phi, okay, to do the regularization, okay. So you can use many things, okay. So we propose this model here, okay. Now, so far, so what we have mentioned is that it's the simplex case. Basically, what we have mentioned so far is that so between the telescope or eyes here and the thing that you want to observe, we assume that there is only one layer of air moving, okay, between the telescope and the satellite. But in fact, in real case, so the air is in between is actually divided into different layers of air, okay. So here I draw the 2 layers, okay, so of air. So each layer of air will give you a phi, okay. And then the total phi that you observe from the telescope from the telescope to the satellite is actually the summation of this phi, and each layer of the phi is unknown. Okay. Now let me show you some examples. So if you have only one layer of phi, then it look like this. Okay, and then that's what you observe on the waveform sensor. It's the derivative of this in low resolution. But if you have 3 layers of phi, so this is what you will see, okay? And then this is what you observe on your waveform sensor. It's a derivative of all this summation of phi, okay? So then, how do we solve this? Well, it actually is not that difficult. So all you have to do is to work out the physics, and then basically, so what you observe on the telescope, okay, the waveform sensor, is a derivative of all these different layer of phi, okay? And then now because you are moving, so the AI are the motion matrix at the I frame. So because you use multi frames at the J level, okay, at the J level. So well, so you should know that because at different level it's a different height, right? So if you move, for example, if you move the telescope 1 inch or 1 centimeter on the ground level, it can be a several hundred of meter when you are reaching a higher altitude, right? So then this A are different at different level, okay. But then well, the main important thing is that so you control the motion of the telescope, right? So you know all this AI, okay. Now once we have this model, then now the question is, given this measurement, how do we find this? Well, in fact, this is still a least square problem, right? So you just write it out, it becomes this, okay? So these are your measurement on the waveform sensor, and these are the different layer of phi that you have to find, okay? And then now you can regularize them directly, okay? And this is still a L1, L2 model, and it can be solved by ADMM easily. And then once you have found all the phi, then you just sum them together. And then now you plug it into this, and then you get your Ponsberg function. And then now you can go on to debug it, okay? So now let me show you this idea. So how good this is, okay? So we use the data generated by in Jim Nagy's paper. So basically, we generate this phi. So then we can measure how accurate our result is. So this phi is generated according to some physical model of atmospheric turbulence. So we generate this phi. This is a true phi, and then we take the x direction derivative and y direction derivative according to the Strack-Hartmann's waveform sensor. And then we move the telescope. Okay, we move the telescope how many times? 16 times. Okay, and then we downsample 4 times, and then we get supposedly the waveform sensor measurement. Okay, and then from this one we want to get back the phi. Okay, so we have 16 of this, and then from this 16 of this in the x direction and 16 of this in the y direction, we want to get back this one, and also the phi star. Okay, so that's the test. Okay. So we have 3 models. The first one is the L2 model, and the second one is the L1 L2 model, And the third one is the combined model. You directly solve for the phi. Okay. So for the first two models, of course, after you found the px and py, then you still have to do the integration. And then for this phi model, once we get the phi, then we get the k. Okay. Now then we can measure whether this k from this phi model, how they are compared with the true k. Because remember, we have the true phi, so then we have the true k. Okay, so we can compare this error. Okay, and this is the result. So here is the one single layer. The seeing condition is a measurement to tell us whether the sky is the turbulence is very big or small. Seeing condition equal to 45 is very bad. Okay, so it's a very bad evening to observe the sky. But in any case, so you see that here, so we have 16 frames, and then these are the relative errors in the point spread function. So you see that for the L2 model, that's the first one, the first model. So then the error is actually very big. We have like a 30% relative error in the point spread function. Okay. So and then even if the L1, L2 model, so it's still very big. We have a 25%. But if you use a combined model, so directly solve for the phi, then we have like a 5%. We also have used the try the 3 layers model. So this seeing condition is much better. Now it's 20, okay. But then still you see that so these two are very big errors, but this one is still better. Okay, so 10%. Okay. But then now you will ask, okay, so now we see that the errors in the K is better, but how good it is in getting back the image, okay, so the image that the satellite image, and then we also test this. So remember that we have the true phi, so we have the true k, okay. So now we use this as testing satellite image, and then we bury it with the true k, and then add some noise, okay. And that's what we get, okay, for the seeing condition 50. So that's how you get. So this is true. This is the true image, and then you bury it with this turbulence. And then that's supposedly what you observe on the satellite, okay, on the telescope, and then you want to get back this, okay. So this is obtained from this, okay, by using this, okay. Now, of course, we have 3 different computed K from 3 different models. Now we can use that to given the G, okay, we can use this what you compute, okay, to get back the F. We use a total radiation for the recognition, and then we see that how this F is compared to this true one, okay. So let's see, okay. So this is the true image, and this is the bird image. This is supposedly what you observe on the telescope, and you see that, okay, here. So because we have the true point spread function, actually we can use the true point spread function to bury it, and then that's what you get, okay. So of course in practice we cannot do this because we don't know the true point spread function, but because it is a simulation we can do that. So then you see that if we indeed have the true point spread function, then we can get back a very good result. And you see that all this fine antenna or this small antenna, you can basically see that, right? But then it is assumed that you know the true point spread function. But in fact, in practice, we don't know, right? We have to depend on the 3 models to get us the point spread function and then debury it. So this is the first model, the L2 model. If you use the L2 model to get the point spread function and then debury this image, okay, here, then that's what you get. So you see that now, well, basically you only get the big structure of the satellite. We don't see any of the fine structure. And the point, the PSN now is very low, okay? So if you use the L1, L2 model, it's still it's a little bit improved, right? Because the point spread function is a little bit better, right? This one has a 30% error. This one has 25% error. But using R1, we have like a 5% error. So you see that now we get a much better result, okay? Very close to the one that you supposedly you know the point spread function, okay? And the fine detail are some of them are here, okay? And we also tested for the 3-layer case, so the true image, and this is the blur image. And then if you have the true point spread function, then you can still get a reasonable result. But if you depend on the model to get the point spread function, then the L2 model give you only the big structure, similar to for the L1, L2. But then for the TV model, then now you see much better result, okay? So that's so far for the moving telescope. But then of course, for those big telescope, for example, this one is the one that we are going to build in Chile. It's the largest telescope in supposed to be, okay. But this one, of course, you don't want to move the telescope. But then you think about it. So in order to get the high resolution image, let me use this example again. So of course, we want to get multiple frames to get this number. Of course, one way is that so we move the telescope, we move the camera. But another way is that so we don't move the camera, we move the bookshelf, right? So it's the same thing. Now if we don't understand this, then well, actually, so we don't have to move the telescope because the air actually itself is moving. So we test this idea. So suppose that we have 3 layers here. So different layer have different phi, right? So it's at the time 0. So these are different layer. And then this is the total phi, okay, total wavefront. Now suppose that with this air, so different layer, they are moving in different velocity, okay, in different direction with different speed. Now suppose so they are moving like this. Then after 5 seconds, what you observe on the wavefront sensor is something like that. After 10 seconds, what you observe on the wavefront sensor is something like that. Now the question is, can we combine all this to get the a higher resolution wavefront? So the idea is that if you know the this velocity, in fact, yes. Okay, so this is the outcome. We construct the high resolution wavefront. Okay, the phi. Okay, and this is the true phi. So you see that the error is actually very small. If you look at the numerical result, so actually it's very small. Okay, it's like a 2%. Okay, so you see that so it doesn't matter whether you move the telescope or not. Okay, so because the air is moving, so if you know the velocity of the air, then you can also do a good job. Now let's move this one step further. Okay, so this is the largest telescope that we are going to build. Okay, so it's by the European actually. So it's a very big camera. The telescope is 39 meter, and it will start taking picture in 2025. And even for this, the world going to be largest telescope, the wavefront sensor, you see that the resolution is around 80 to 90. Okay, it's very low resolution. So then they for this telescope, it also needs some kind of high resolution imaging. Okay. So now let me tell you exactly how we can do this for this big telescope. So in order to understand this, we have to understand what is the closed loop adaptive optic system. So far what I mentioned to you is what we call the open loop. But now I'm going to tell you the closed loop. Okay. So a closed loop system is like this. Okay. Suppose I have a wavefront coming in, okay, to the telescope. Now the wavefront is not measured directly by the wavefront sensor. The wavefront first go through what we call the adaptive mirror, okay, or deformable mirror. So the deformable mirror is something like so trying to emulate the incoming wavefront from the past data. Okay, so that you try to do something similar to this one, but then using past data. Now, if we can measure the, if it is accurate, then basically, so we would subtract this one from this one. Now, if this is estimated accurately, then what we have what we call the residual wavefront should be 0, right? So it should be 0. But in fact, of course, usually we cannot do exactly exact measurement or prediction using the past data. So that's why we get a residual like this. Okay, so not all of them are 0. In fact, there are some of them are very big. Okay. So and then this residual waveform is passing through the wavefront sensor. So you see that after the deformable mirror, the wavefront sensor only measured what we call the residual waveform, not the original waveform. Okay, so this is called the closed loop. Okay, and then this residual wave, this wavefront sensor is measuring this one, but using a low resolution, right? So we get this. Okay, and then using this, then we try to update the deformable mirror for the next time step. So this is the structure of this closed loop adaptive optic system. So so because the notation is getting complicated, so I will use this notation, okay, or convention. So I will use capital letter, for example, this one to denote high resolution images. Okay, I will use a small letter, for example, this one to denote low resolution images. Okay, for example, this one. Okay, So now let me say something more. So you see that so the incoming waveform at the time t is coming. So the deformable mirror is trying to emulate this, and then we subtract this one from this one. Then we get the residual waveform. The residual waveform. This is a picture of the deformable mirror. Okay, so just to show you. And then this residual waveform is high resolution. It passes through the Waveform Sensor, and then we get the low resolution residual. And then from this low resolution residual, then we try to decide on the deformable mirror for the next time step. First low resolution, and then high resolution, and then we put it here, and then we repeat the process. So that's how that's the whole process. Now, so let me show you the grid pointer to make sure that you understand. So the phi is coming from this, okay, and then for the whole region, and then this is the wavefront. This is the aperture of the telescope, okay, and then the green point are the high resolution point, and the blue point are the low resolution point. And on the telescope, so the light, the most important thing we have to remember is that so only this is stored because the data are huge, so they don't store everything. They only store this one. And then so our idea is that so if we are only storing this one in the computer, so can we get it back offline, the high resolution phi t offline? So after we store all this, okay. So our idea is that so we have this one. So we try to reconstruct the high resolution deformable mirror measurement, and then we also get the this low resolution residual, and then from that we reconstruct the high resolution residual, and then we add these two together, then we get phi t. But the question is, how do we get from this step to this step, or this step? Okay. So the idea is that we use a multiple frame. Okay. Again, so we use multiple frame to do this. Okay. And then of course we also assume we have a Taylor Fulton flow hypothesis. That means that during this time step, the phi does not change much. Okay. Okay. And so basically, so we try to get this. Okay. So in order to do that, so I have to tell you more. So exactly what's the whole procedure? Okay, inside the closed loop. Okay, so how do we get from the DT the deformable mirror from this time step to update the deformable mirror on the next time step? So these are the steps. Okay, so first we get this this one, and then this is a low resolution. So now we have to extend it or upsample it to a high resolution. Now this function is actually fixed by the structure of the deformable mirror. We cannot do anything. Okay, so this function is given. So from the low resolution to the high resolution, this function is given. Now remember that so once we have this, and then we subtract a phi t from this, then we get the residual waveform, and then the residual waveform is passed into the waveform sensor. You remember the formula I mentioned in the first part of the talk. Then now we have the downsampling of this residual waveform, and then we pass it through the Hartman operator, which is the dx dy that we mentioned before, and then we restrict it into the aperture of the telescope with some unknown noise. Then we get the waveform sensor measurement, okay, for the residual waveform gradient. Okay. Now once we have this, now then remember this is the high resolution one. Then after downsampling, that is the low resolution one. So we have the measurement from the waveform sensor. Then we solve this. Okay, we solve the equation for this one. Okay. Once we solve this, then how do they update this? So basically they add it to this, and then with some damping factor. Okay, so usually it's close to 1, but smaller than 1. Okay, and then we add it to this. Then we have this. And then once we have this, then we can go back, right? So, and then we do the whole step again. So as I said, so in the whole process, so we only store this and this. We don't store the others because they are too big, okay? So now if once we know this whole thing, then now we can propose our model. So this is our model. Oh, sorry, okay. So this is our model. So our model is that, so suppose if we have this this one stored in our computer from time t0 up to time t. And then from this, we want to find all the phi t in between t0 to t. And also we build in the velocity. So we don't assume we know the velocity. So we build in the velocity as unknown. Okay, so we build it. Now, for this model, we assume that is single layer. So it's easier for me to explain. Okay, so this is our model. How do we find this all phi t? Okay, and also the v. So if you look at this one, so phi t minus phi t dm, what is this? So this is the high resolution phi t. Okay, and then how do we get this one first? Okay, this one is from this one, right? So the inference functions. Remember, this is one we have in the computer, so we can find this. And once we have this, then we subtract this, the high resolution one. Okay, and then the high resolution one passing through the downsampling, passing through the waveform sensor, and then the aperture, and then that we become the waveform sensor measurement. But we don't store this, right? But how do we get it back? So remember that. So we get to go back here. So how do we get this back when we have the this one or this one? Okay. So basically, you see that or this one. Okay. So basically, this one can be obtained from this one, subtracted this one, divided by alpha, right? So then we can just put it here. So because we have these two, so then we can get this measurement back. Okay, so we put it here, and then we have some regularization. So you see that. So basically, so here we can solve this because we have this. Okay, and then so here we solve all the phi t with the assumption that they are the phi is moving in a constant speed. Okay, from time zero up to time capital T is moving in a constant speed velocity of constant velocity v. So then we can relate them all together. And here we use, as I mentioned before, we use a covariant matrix of phi using some physical model. So we use this as a regularization. And then now this model is with v is known, then of course this model is easy. So it's a fixed it's a convex model. But then because v is unknown, so this model is highly nonlinear in terms of v, right? So when we solve it using ADMM, but then we linearize the submodel, the subproblem v. Okay, so this is the model for the one layer. Okay, but then now we can well, if you understand the one layer case, then you can, if you have a 3 layers, for example here, and then if you assume each layer is moving in a constant velocity, then you can build the same thing, right? As we did before, right? So basically, the total phi is the summation of each of these unknown phi, and then you can build up the same one, and then also assume that the velocity Vj, and then you can also find the Vj, okay, for each level, and then you solve for this, okay. So now let me show you the numerical results. Okay, so here we use this very standard model. The very large telescope. Okay, it's 8 meter. Okay, it's also in the Southern Observatory, European Southern Observatory. So we use their parameters. Okay, and here we try to upsample by 4 times. Okay, and then we test the different cases. Okay, and for first 3 tests, actually we use this we use this velocity. Okay, and low flux meaning that the photon coming into the telescope is the number of photon coming to the telescope is low. Okay, so that means you may think of it as high turbulence. Okay, and this one is low turbulence. Okay, and then for the line layer, we use the very standard profile. Okay, so these are the different layers parameters. Okay, so usually people test it like this, and then we use 20 frames. Each frame is separated by 2 milliseconds, so altogether is 40 frames, 40 milliseconds for the whole procedure. And these are the results. Okay, so the red curve here give you the error in the phi. If you just use just a bilinear upsampling to get this high resolution residual waveform, and then from that you get the phi t. So you see that the error can be very big. Okay, can be very big. And then the next one, the purple one, is the one that one. Okay, so we assume that we just fix wind velocity. So that means we don't know the wind velocity, but we just assume it to some value. And then you see that if you don't have a good wind velocity, then error can be big. And then if you have the exact wind velocity, of course we don't, right? But this is a simple this is a simulation. Then we do. Then this is the error. Okay. But then if you use our algorithm or model, which we try to compute the velocity you build into the model, then you see that the error is basically the same. Okay. So basically we get the true velocity. Okay. And then these are the image result. Okay, so if you use if you just use bilinear upsampling, then you see that the residual wavefront is very big. Okay, so then you basically you don't get any good result. And then if you have exact wind velocity, then the wavefront gradient is very small. Okay, and then this one. Okay, this one is if you do not load the wind velocity. And then I also give you some image. So this is what we store. Okay, and this is I don't know. Actually, it's moving. Okay, so this is the true wavefront. And this is what we compute, okay, using our model. So you see that they are basically very close. And this is what we store on the computer. And then this is a true wavefront, and this is the computer wavefront, the high resolution one. And then I give you two. This is the third test, the 2 layers. Okay, and then this moving slowly. Okay, and this is the last one. This is linear. Is it moving? No, don't know. I'm not sure whether it's okay. Yeah, it's moving very slowly. Okay, but you see that basically is kind of good. Okay, compared. Yeah. So we have published this result last year in SIM imaging. Okay. So this is also some result to show that well, here is that, so if your initial if you have some error in the in your initial velocity, okay, so and then you if you don't change it, okay, and then you use your wrong initial velocity, then your the relative error in your phi can be very big. Okay, so something like that. Okay, so if you have 40% of error in your initial velocity and then you don't fix that, then your error can be very big also. But then if you have a very big error in the initial velocity, but then if you use our model, then our model will find the correct velocity, and then so the error is kind of very small, okay, compared to what this. And this is the conversion results of the velocity. So here we try 8 cases. This is 1 layer case. And then we try different initial velocity. You see that they all converge to the true velocity. And this is the 2 layer model. We try different, so these are the 2 velocity for the 2 different layers. And then we try 8 different initial velocity. And then you see that they all converge to the true velocity. Okay. So let me conclude. So basically, we what I mentioned here is that we can use super resolution techniques to get high resolution phase. Okay. And then once we can get the high resolution phase phi, then we can get a better point spread function k using the Fourier optic formula. And then once we have a better k, then we will get a better deeper image. And what our model proposed now is that we don't need additional storage, because we just use what is stored offline, and then we can get the better phi from that. Okay, and then the wind velocity, now we don't have to we can estimate. We don't have to try to get it using some other means. Usually people will just send a balloon up to the different layer of atmosphere to try to measure their velocity, but now we can actually build it into the model. We don't have to estimate this. And of course, here the model, you may say that is still is the first model in this direction. So I suppose that should be a better solution model, okay, for in the future. And here we mentioned only telescope, but of course the same idea can also be extended to microscopic images, where we also have this kind of lateral guide star in what they call it fluorescent beads, okay, in microscopic images. So hopefully the same idea can be worked there. So this is what I have to say. Thank you very much.